Hello, this is Rob Reiner from Tachyum. Today, we're going to demonstrate a new feature that we've implemented on our Prodigy Universal Processor called DRAM Failover, which is running on our Prodigy hardware emulation system, which runs the actual Prodigy design. This is an integral part of our RAS strategy and allows us to recover from die failures within our memory subsystem and adapt our memory processing to seamlessly work around the failure. Today's large, highly scalable data centers typically have thousands of processor cores with potentially millions of memory dies and require high availability and resiliency. Prodigy's advanced DRAM failover feature ensures the high availability that is critical for business continuity. In order to support this capability, we have several ECC options built into our system that we can invoke as needed, including monitoring logic in our DRAM interface so that we know when one of our dies has failed, with all logic built into the Prodigy device. We've pre-booted Linux and now we'll start a demonstration, which begins with the following. Initializing the test conditions, running a standard Linux routine to generate memory traffic, and looking at the result. Looking at the design that's up and running on the chip, we're going to be consulting some of our machine check and recovery registers, which monitor various functions within the die. At this point, we're using them to monitor four aspects of the memory subsystem: the number of accesses to the particular DRAM subsystem we're looking at, the total number of DRAM ECC errors that are detected on those accesses, measured in 8-bit symbols, the number of times we encounter two errors in one word, the double error case, and the number of triple errors that are encountered in a single read operation. First, we'll run a test case with no memory errors inserted. As you can see, there are no errors encountered. Now we'll turn on the error insertion logic, which will force an error on every read. As you can see by reading the MCR registers, the total number of accesses and the number of ECC errors are equal. So for each access, we forced one ECC error that was corrected. We'll now change the error insertion logic to insert two errors. That's two independent 1-byte errors within each word which is read. This is the type of error that we would expect to see if there is a single bad die selected during a read operation. As you can see, the total number of errors is now twice as many as the number of accesses, and those accesses are all identifying as double errors. Again, this is what we would expect to see if there is a die failure, the equivalent of 2 bytes, two 8-bit symbols in error during every read operation. This is the limit of the device's ECC correction capabilities in this mode, which is what is most commonly used. Any errors beyond this point become a data loss. We can recover from two hard errors, but any further errors would cause an unrecoverable data error. There's simply no more ECC to get the data back. However, with our DRAM failover, we have an additional mode that allows us to now work around this error condition if we know the location of the bad die. In this case, we're able to configure the ECC engine to take advantage of that, extending our correction capabilities. In this case, we add intermittent third errors on top of the double error cases. Looking at the resultant counts, we now see triple errors in addition to the double errors we saw earlier, and the system continues to run normally. At this point, we would switch ECC algorithms to use another mode that will optimize the data during write operations to work around the failed memory locations, further augmenting the system resilience. We might discover the bad die during reads, but we would subsequently avoid the die during writes, maximizing the reliability and availability of the Prodigy-based systems. That concludes our demo. Thank you very much, and stay tuned for future Prodigy milestones.